Hi there, it's Dr. Maxwell, and I had some questions about example 2 from the lecture on proofs involving sets. So I'm going to go over a few things. First, let's just look at the Venn diagram and convince ourselves that this is true. So let's shade B intersect C in red. That would be the overlap of B and C. And remember, this is our universal set U. And I'll shade A in green. If you don't have two colors, you can do these things in different orientations, like one vertical, one horizontal. Okay, so now what are we looking for? We're looking for A together with the intersection of B and C. So we want all the shaded region. So it's this whole thing, sort of funny looking shape. If I now shade all of this in blue, that represents the set we're talking about. So when it's or, you want any area that's shaded. When it's and, we'll see that in this situation. We're going to look for the overlap. So to get started with this one, we may need to do two drawings. And we know these are the same, but let's pretend that we don't. This is one of our distributive laws. Okay, so I'll start by shading A union B in purple and use horizontal lines. So that's everything in A together with everything in B. So you want to shade the A circle and the B circle. So that's A union B. And then I will shade A union C in red, and I'll also use a different orientation. So I want all of A and everything in C as well. It's an or. So shading all of A and all of C. Now this picture is a little harder to interpret. We're looking for anywhere that has both purple and red. That's what I mean by the overlap. And if you're using different orientations, you want everywhere with the vertical lines and the horizontal lines. So let's see where that happens. You'll notice I'm outlining exactly the same shape. So we know they're equal. Now, the question came towards the end of the proof when I was showing this relationship. So let's go through this part again. Okay, so to show this, we let x be an arbitrary element in the set on the left, and then we show that it has to be in the set on the right. So you just have, all we have to go on is, what does this mean about x? Well, then x is in A union B, and x is in A union C. Okay, now, since X is in A union B, what does this mean? It means X is in A or X is in B. And since X is in A union C, because remember X is in both of these sets, X is in A or X is in B. Now, if you think about this, either X is in A or X is not in A. So this is not really in the proof, but this might help explain that last bit of the proof. So if X is in A, then it's in this union, right? Because it only has to be over here or over here. We have to show that it's in one of those two places. So if X is in A, X is in A union B and C. So that's okay. Well, what about the case if X is not in A? Because that's an or statement. It might be possible that X is not in A. Then where is X? X is both, oops, I have a typo here. If X is not in A, then X has to be in B and it has to be in C. Because if it's not in A, from here we get that it's in B, and from here we get that it's in C. So and again, X is an element of A union B and C. So that is because we know either X is in A or not in A. If it is in A, then it's already in the union and we're good. If it's not in A, well, what do we know? We know it has to be in C and we know it has to be in B. So that's how I got to there in that proof. So I hope that helps with that. And we also had a question about letter D in example 3. So you're asked to decide whether this is true or not. And really, you should know right away that this is false. Why do you know it right away? Because of De Morgan's laws. And you don't need to memorize the distributive laws, but do memorize De Morgan's laws. In our book, they're written like this. That the complement of the union is the intersection of the complements, which is very strange, but I'll talk a little bit more about this in a minute. And the complement of the intersection is the union of the complements. Now, compare this to De Morgan's laws for logic. So when you're negating the or statement, you have an and statement. And you see how this negation applies to the whole statement, just like this complement applies to everything. And here, now the negation just applies to the individual pieces, and we have this symbol that looks very similar. So this can help you remember which way these things go. The complement of an and statement, the negation is going to be not P or not Q. And we have the same sort of thing going on. This applies to everything inside there, And when you get rid of the parentheses, it applies to P, it changes the and to an or, and it applies to Q. So if you look at the notation I'm using with D, it's even more obvious perhaps. This does not equal A complement union B complement. In other words, De Morgan's laws using this notation what does it look like? To me, it's a little easier with this kind of notation because it's so much similar, so more similar to what happens over here. It's going to be the complement of A and the complement of B. And then with the intersection, you get the complement of A or the complement of B. Do you see how they're analogous to these situations over here? Now, so we know this is false, and we're going to look at a picture to convince ourselves it's false also. So how would I do this? Well, we just draw the two pictures. We only need two sets. So what does A union B complement look like? Well, that's everything outside of A and B. Now, I think our book tries to do this, well, never mind. It's also equivalent to you take away the set A union B. Sometimes that can be useful. All right, so what does this one look like? Well, that one's going to be a little more complicated. Let's see what it looks like. Here's A, here's B, and this is a union. So I'm going to shade A complement in red. That would be everything outside of A. And use horizontal lines. And keep in mind this is a union, so we will want anywhere that gets shaded. Already you can see they're not the same because of that shading in B. This B doesn't have any shading over here. All right, now do B complement in green or a different orientation. That's everything outside of B. And you see how we're going through A because this part of A over here is not in B. Now the union, anywhere that's shaded green or red. So this includes everything except the intersection. So this picture, A complement union B complement, is the same thing as A intersect B complement. It's definitely not an equality here. Now let's see if we can come up with a counterexample. So I'm going to try, and I'm just doing this on the fly, see if I can make something that will work. The key is to put a number everywhere. So I'll just start putting the number 1 there, the number 2 here, the number 3 here, and the number 4 there. Now, A union B complement is the set that contains the number 4. Do you agree? So 4 is an element of A union B complement. Now, A complement union B complement, well, A complement includes 3 and 4. So this is the set contains 3 and 4. And together with B complement, which contains 1 and 4. So we just need to put the 1 in there. And so these two sets are not the same. Because this is the reason they're not equal. A complement union B complement is not a subset of A union B complement. Of course, A union B complement is a subset of A complement union B complement, but that's not what we were looking for. We need both directions to get equality. So for counter examples, the key is, for me, just make sure you put a number at each disjoint region of your Venn diagram. What do I mean by that? Let's get rid of the circles. There are 4 distinct regions. We'll do 1, 2, 3, 4 when you have 2 sets. So what are these regions? Let's see. So we can describe these regions. What is the region represented by number 1, Roman numeral 1? Well, that's A intersect B. The region in number 2, that's A minus B. The region in number 3 is B minus A. And the region in number 4, well, you can describe it in several ways, but I'm going to say it's U minus A union B. It's also the complement of the union, but these are all what we call disjoint. There's no overlap. And that's important to understand. Okay, so I hope that was helpful, and bye for now. Let me know if you have any more questions.